Good morning, good afternoon, and good evening. Welcome to the Crazy Hat Chemist. So here's another video here. Today is what video are we working on today? That is the covalent bonding worksheet number 1. All right, so really and truly, before we get started on this worksheet, you need a number of items handy. So number 1, what are you going to need? You're going to need a periodic table. That is going to be critical. Number 2, you're going to need my handout here, and that is, what is it? It's the covalent bonding handout number 2. Okay, so you're going to need that. You are also going to need a model kit. So model kit would consist of the following, and let me open one up so that you are going to see what we've got. So here is going to be a model kit. And in my model kit, I have made the key to building these models right here. And so this gives you everything that you need right there in this model kit, as well as this key. All right, so without further ado, let's get moving on this here worksheet. So I'm going to zoom in here just a little bit. This is the entire worksheet. Remember, you are watching the Crazy Hat Chemist. That is me. I made this worksheet. I designed this. And I am teaching you real chemistry so that you can actually be successful in college in the future and beyond. All right, so we're going to zoom in a little bit here so that we can see just certain sections of this. What we are interested in is what you see before you here. Okay, so I do have an example problem, and it's the name of the compound is methane. The formula of the compound for methane is CH4. That is the simplest hydrocarbon that there is. And then we're going to add the total number of valence electrons and get the number of electron pairs. So here's how you do that. So what we're going to do is we're going to take our periodic table here. And what we need from our periodic table is the number of valence electrons. And depending on the periodic table that you have, it is written right there on it for you, or you can derive it from the information that is given on the periodic table. So for example, on this periodic table that we're using here for my general chemistry class, this is column number 1. That's 1 valence electron, and you can see that right here with the 1A. Column or group number 2, and you can see that's with 2. So in this column, how many valence electrons in here? Every single element has 1 valence electron. In this column or group 2, every single element here has 2 valence electrons. For the activity that we're doing here today, we're going to skip the transition and intertransition elements. The intertransition elements are the F block that you do not see here, and the transition elements are the D block that you see right here. We're going to continue on, and there are 3 valence electrons that corresponds to that 3 on the 3A. There are 4 valence electrons that corresponds to that 4 and that 4A. 5 valence electrons that corresponds to that 5 on that 5A. 6 valence electrons, and that corresponds to the 6 on the 6A. 7 valence electrons corresponding to the 7 on the 7A. And then 8 valence electrons corresponding to that 8 on the 8A. Helium does not count in this activity. The other thing that you need here is the following. You need to know what is the most electronegative element. So I'm just going to write valence electrons. So the valence electrons are in the red, and electronegativity. So electronegativity, what is the most electronegative element? That would be this element right here, and that is fluorine. So fluorine is the most electronegative element there is. And that means that the farther away from fluorine, for example, francium is the farthest away from fluorine. That would be the least electronegative element. Okay. All right, perfect. So you're going to need to know this for your background information. Now let's take a look at the problem that we have at hand. We have carbon. So how many carbon atoms are there in this formula? There is a 1 right there that's assumed. So that means that there's 1 carbon. And how many hydrogens? Well, I'll highlight that right here. There are 4 hydrogens. So we're going to count up the total number of valence electrons here, and there's 1 carbon. So I need to find carbon on my periodic table. That is right here for carbon. How many valence electrons in carbon? It's in group number 4A, 14, or there's 4 valence electrons. So that's why there are 4 valence electrons in carbon, and that is right there. How many carbons are there? There's 1 carbon at 4 valence electrons. Then hydrogens. Hydrogen is right here. It's in group 1A, and that is group 1, and there's a 1 valence electron in hydrogen. So that means there are 4 hydrogens, 1 valence electron in each hydrogen. So we're going to do the math here. That is 1 times 4 plus 4 times 1. That's a total of 8. Then what we're going to do is we're going to take those 8 total valence electrons and we are going to divide by 2. Why are we going to divide by 2? We are always going to divide by 2 such that we get electron pairs. So there are a total of 4 electron pairs here. Okay. Sorry for the lawnmower in the background. Hopefully you can get over that. All right. All right, so now what we are doing here is we are going to take a look at how to do the Lewis dot structure. And you can actually see the Lewis dot structure that I've drawn here. That's just as a reference. So like I said, you actually need this worksheet right here. It's the covalent bonding handout number 2. What we are doing is we are doing this like lower 2/3 of this worksheet. So let me fold this so that I can show you how this works. Exactly. Okay, so here we are. We're going to actually follow the rules on this. And here is another video that you should watch on YouTube. It's in the Crazy Hat Chemist. It's in the Honors Chemistry 6 section. That is the bonding collection. It's bonding number 11, Lewis dot structure rules. So these are the sequential steps for drawing Lewis dot structure. So if you follow these rules in order, you'll be good to go. So here we go. So the first thing that you're going to do, which is step number 1. Step number 1 says sum the total number of valence electrons. There is no ownership to electrons. Follow the rules below for placement. So that means that I just summed up the total number of valence electrons. We're going to be working with pairs because it's going to be much faster in the future, guaranteed. 1A says add for each negative charge of an ion and subtract for each positive charge on an ion as noted above. We don't actually have to do that on this problem because this problem of methane is neutral right there. There is no charge in that upper right-hand corner. So check on number 1. Number 2, determine the central atom. This is the least electronegative element. However, it cannot be hydrogen because hydrogen cannot branch. The central element is designated as A when determining the geometric shape name. So let's do number 2 here right now. So what we need is we need to go back to our periodic table. We're going to find the most electronegative element, and that is most certainly fluorine. So fluorine is the most electronegative element. Now what we're going to do is we're going to take the elements that we have at hand, and that is carbon and hydrogen. And the real simple method here is what we're going to do is we're going to take that carbon and we're going to draw a string between the carbon and the fluorine. Okay? And so here is my string between the carbon and the fluorine. And we're going to measure that distance. And then we're going to take a string and measure the distance between the hydrogen and the fluorine, because there are only 2 elements in this compound of methane, CH4. There's a carbon, there's a hydrogen. So the distance between the carbon and the fluorine is the distance if you take a piece of string or a ruler. And then for hydrogen, wait. Hydrogen is never the central element. So by default, from this rule here that I've spelled out for you, It says determine the central atom. This is the least electronegative element, which is the one that's furthest from fluorine. However, it cannot be hydrogen. Since it cannot be hydrogen, it must be the carbon. So the first thing that we're going to do is place the carbon in the center. All right. So now we have done rule number 2. Now we're going to read rule number 3 so that we can carry on here. Number 3 says place additional atoms in the positions of the faces of a clock, 3 o'clock, 6 o'clock, 9 o'clock, and 12 o'clock, or like a compass, north, east, south, and west, surrounding the central atom. These are designated as X when determining the geometric shape name using the Vesper theory. Okay, so excuse me. What we're going to do is we're going to place these elements kind of like the face of a clock. So I'll just draw this, dash this in pencil here so that you get this idea. Okay, so the elements of which we have remaining are 4 hydrogens. That goes in the 3 o'clock position, the 6 o'clock position, the 9 o'clock position, and the 12 o'clock position. Perfect. All right, now we're going to do the next thing here, the next step. So we've done 3. Now we're going to do 3A. So this is placement of electrons. We're going to place a pair of electrons between the central atom A and all surrounding outside atoms X. So the A is the carbon, the X's are the hydrogens. We're going to place a pair of electrons in between these, and this is what we do, just like that. Just as a note, we will not do the following: carbon and a hydrogen, and you can kind of see that one that I just did in 3 o'clock position. We cannot place the electron dots like that. That is an absolute no, okay, by convention. So we're going to do 3 o'clock, 6 o'clock, 9 o'clock, and 12 o'clock. And so we have placed our 4 pairs. That's 1, 2, 3, 4 pairs of electrons. Okay. What doesn't belong here are the pencil marks that I've drawn. And so I'm going to erase the pencil marks. And what remains is exactly what we have over here on the left-hand side. What we're going to do is we're going to replace these dots with solid lines. Each line represents a pair of electrons. So now I have the Lewis dot structure for methane CH4. Okay, we're going to continue on here. We can't actually do B. We're going to come to B in another one, but 3B is if electron pairs remain, of which they don't, so we don't do that. C is if electron pairs remain, they didn't for B, so they certainly don't for C. So we got to do number 4. We're going to verify the octet rule, the vast majority of elements, and the duet rule for hydrogen only. So here's how we do this. What I like to do is circle each element. I do this in my head. I don't actually do this on paper, so I'm going to do it in pencil so we can erase it. So we're going to circle each element and the electrons that surround it. That hydrogen has 2 electrons. That is a duet. That is the rule for hydrogen. This 6 o'clock hydrogen has 2 electrons. That is a duet. This 9 o'clock hydrogen has 2 electrons. That is a duet. This 12 o'clock hydrogen has 2 electrons. That is a duet. And this carbon right here has 2, 4, 6, 8 electrons. That is an octet. Boom. That's perfect. The rules have been applied and verified. So we have verified the octet rule, vast majority of elements, and the duet rule, and that applies to hydrogen only. There are exceptions to the rule. We won't check that for right now, but carbon, nitrogen, oxygen, and fluorine must obey the octet rule in all circumstances. Number 5 says, to satisfy the octet rule, multiple bonds, double or triple, may be necessary by sharing electron pairs. Well, we didn't need to do that on this one since these all have an octet. That is, the carbon has an octet and the hydrogens have duets. Perfect. Then the next thing is that we are going to do the next column, and we're going to name the shape or the molecular geometry. In order to do that, we're going to go to the top of this worksheet. And if you wanted a further explanation of this top of this worksheet, you're going to watch my video on YouTube. It's The Crazy Hat Chemist. That is me, because I'm crazy. I wear hats on Fridays, and I'm a chemist. And you're going to go to the Honors Chemistry 6 section of my videos. That's the playlist. You're going to go to the covalent bonding section. That's that playlist. You're going to go to bonding number 28, molecular geometry. And this data table will be there with an explanation therein. Okay. So here's what we're going to do. We are first going to solve for the ax. So we want to get the ax. So the ax is right here, ax. So as we stated earlier in drawing the Lewis dot structure, the A is the central element. What's the central element? C. So there is an A that's representing the C. How many central elements are there? There is only one, so that's actually A1. The X's are the outside elements physically attached to the central element. So there are elements that are physically attached to the central element. That would be this 3 o'clock, 6 o'clock, 9 o'clock, and 12 o'clock hydrogens. How many of those are there? 1, 2, 3, and 4. So there are 4 X's. So it's AX4. Are there any E's? E's would be lone pairs on the central element. There are no lone pairs on this central element. There are bonding pairs, but there are no lone pairs. So there's not an E in this. So AX4 is my axe-like structure. I'm going to go to my data table right here. I'm going to find AX4. Okay, it has 4 bonding domains, 0 non-bonding domains, that's lone pairs. The name of the shape is tetrahedral. Therefore, the name of the shape is tetrahedral right there. To get the bond angle, it corresponds to the name of the shape and the ax. So we just got the ax at AX4. We got the shape of tetrahedral. We're going to get the bond angle of 109.5. That's how we're going to get 109.5. Perfect. Now we're going to go to the next one here, and the next one is the molecular polarity. It's either going to be polar or non-polar. So how do I get that? Well, we're going to ask the question here of how do we build this molecule? So how we build this molecule is we need to pull out our molecular kit here. We're going to look at our rules and our key to this. And we have a carbon, that's a black with 4 holes. That is right here. I'm going to pull that out. We have a hydrogen. That's a white with 1 hole. There are actually 4 hydrogens. So I'm going to pull out 4 white circles. And then somehow I need to attach these, and I'm going to use these short stubby sticks. For those, these represent a pair of electrons that are bonding electrons. We'll pull all that out of the way. And let's get this straightened up again here. Perfect. All right, so what we're going to do is we are going to put all this together and make one molecule. So here we go. There's only one way to put this together, and you just got to stick the pieces together. It's kind of like building a Playmobil set, or not quite Legos. It's a little bit different compared to Legos, but it's kind of more like a Playmobil set. So here we go. And perfect. That is the molecular model of methane. The carbon, the black item in the middle is the carbon. The white circles are the hydrogens, and the gray sticks are the pairs of electrons that are bonding between atoms. So that means that since this shape is tetrahedral, that means that the white things are at the apex or the corners of the tetrahedron. The bond angle of 109.5 is here, 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 and here, here, and here. So everything has bond angles of 109.5. So now what we're going to do is we're going to figure out, is this polar or non-polar? And how we figure that out is we look at, I'm going to give you a real simplistic way of looking at it. Are all the things attached to the central element the same, or are they different? So That is this the same as that? Yes. 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 So they are the same. If they are the same, then it is what's called symmetrical, and that would be nonpolar. Nonpolar is the answer that we're looking for here. Okay, so this is a nonpolar molecule of methane. Okay, that means it has symmetry to it. It's a symmetrical molecule and it is nonpolar. Okay, polarity and nonpolarity, that's a whole different topic as to what that means, but we're just getting that it is either polar or nonpolar. Okay, perfect. We're going to pull this away. Now what we need to do is we need to do the next problem. By the way, in my class, you get a stamp for actually building the model and coming up with all this on this here worksheet. All right, let's go for the next problem and see if we can cruise on a little bit faster now. So number 2 problem is chloromethane. I've given you the formula of CH3Cl. So we're going to find these elements on the periodic table. We're going to find carbon on the periodic table. Carbon is right here. It has 4 valence electrons. So there's 1 carbon at 4 valence electrons. Hydrogen, there are 3 of them, and the hydrogen has 1 valence electron for each one. Perfect. Chlorine, there's 1 chlorine, and chlorine has how many valence electrons? 7 valence electrons. So that's it for the periodic table at this moment in time. We're going to do the multiplication here, then we're going to add them up. So that's 4. That's equal to 4. That's equal to 3. That's equal to 7. We're going to add these up here. That's equal to 14. And what do we always do? We always divide by 2. So that will be 7 pairs. We work with pairs. That's the simplest thing to do. All right, the next set of rules, we've summed up all our valence electrons. By the way, we are following these set of rules to the T. Absolutely, we are following these rules. We just did rule number 1. We summed up all the valence electrons. Now we need to determine the central element. The central element is based on the electronegativity. Okay, and so what we're going to do, what element can it not be? It cannot be hydrogen, so we're going to cross that out. So I have 2 choices here. I have either carbon or I have chlorine. So what we're doing here is effectively drawing a piece of string from the central fluorine, the most electronegative element, to the central of the carbon. From the central fluorine to the central of the chlorine. Which line is longest? Okay, well, this is shorter and this is longer. So therefore, carbon is going to be in the center because it is the least electronegative. All right, so carbon is going to be my central element in the middle. Excellent. Now, remember like what I did before, I put some dashed lines here. We don't actually do that. That's just in my mind, but that gives us our 3, 6, 9, and 12 o'clock positions, north, east, south, and west. So what we're going to do is we're going to place the remaining elements of 3 hydrogens and 1 chlorine around this. And you can start anywhere you want to. I don't know where you want to start. Let's start with, I don't know, a chlorine right here, a hydrogen right here, a hydrogen right here, and a hydrogen right here. So on the back of my periodic table, what we're going to do is I'm going to draw that same exact structure that we just drew. That's a carbon, a chlorine, hydrogen, hydrogen, and a hydrogen. This is one possibility. What's another possibility? We had our central carbon. I could have put the hydrogen here, the chlorine here, the next hydrogen, and the next hydrogen. That is an equally representative sample of that. I could have also had a carbon, hydrogen, hydrogen, chlorine, and then the hydrogen. That is also equivalent. I could have one more, and that is a carbon in the middle, hydrogen, 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 and a chlorine. And that is the other possibility. Each one of these 3 possibilities, I'm just going to highlight this, they must have the carbon in the middle. That is critical because it's the least electronegative, and hydrogen cannot be in the middle. But the chlorines can be in any of the 3 o'clock, 6 o'clock, 9 o'clock, or 12 o'clock position. It actually doesn't matter. Okay, so any one of these four could be perfectly fine. So now what we're going to do is we're going to erase those pencil marks. Hopefully that will make sense to you. And I have never actually put them on there. I just put them in my head. Now what we're going to do is we're going to place a pair of electrons between the central element and the outside element. The central element is A, the outside elements are X's. And instead of drawing dots like what we did here, like what we do in middle school, we're going to actually draw lines. Each line is a pair of electrons. So that would be 1, 2, 3, 4 pair. Perfect. Okay. And now I have used 4 of the 7 pairs. I have to use 7 pairs. I cannot use more. I cannot use less. So one of the things here is that we're going to look at our rules, and now we're going to do a rule that we didn't do on the methane molecule, and that is 3b. If electron pair or pairs remain, place a pair of electrons on the surrounding outside atoms X as lone electron pairs or non-bonding electrons. So, can I place them on the hydrogen? So, for example, if I have, let's say, this hydrogen right here that looks like this, can I place a lone pair of electrons on that hydrogen? Well, if I were to circle that hydrogen, okay, what will I have? How many electrons will be around this? 2, 4. Oh, is that okay or not? Okay, well, we got to answer the question by looking at this, and it says the duet rule applies for hydrogen. So that means hydrogen must only have 2 electrons. We cannot do this. Wrong answer. So this right here can never happen with hydrogen because it already has a 2 with that pair of electrons with that red line. That's a duet. That is a duet. That is a duet. So the next thing that we can do is we can place electron pairs that are non-bonding pairs on the X element, that is the outside element attached to the central element, as non-bonding pairs. So that is 1, 2, 3, 4, 5, 6, and 7 pairs. I have used up all the electrons. Now we're going to verify the octet rule. So I'm going to circle this chlorine. It has 2, 4, 6, 8 electrons. I'm going to circle this carbon. It has 2, 4, 6, 8 electrons. So the chlorine, the carbon, both have an octet, and the 3 hydrogens have a duet. I'm going to erase all the pencil marks that I've done here because that actually does not belong. All right, perfect. You're doing a fantastic job. Let's keep on going. So now the next thing is to get the molecular geometry or the molecular shape. So we're going to write out an axe, right? So we're going to draw out an axe. We're going to pull out the axe, chop it down, baby. So the A is the central element. That is a carbon. That is an A. The outside element or elements are X's. And how many of them do I have? 1, 2, 3, and 4. Okay. The E's are the lone pairs on the central element. Now, I want to just clarify. These are lone pairs on an X. They are not lone pairs on the central element. What would lone pairs on the central element look like? It would look like that. Or it would look like that. But there are no lone pairs on this central element, so I'm going to erase those so that you don't get confused and confounded on that one. So I'm left with AX4. So now what I'm going to do is I'm going to look at my little data table here, and you might have to memorize this for your class. I'm going to find AX4. The name of the shape is tetrahedral. So AX4 does not really tell you anything but the name of the shape, tetrahedral. All right. Now, tetrahedral corresponds to a bond angle. Tetrahedral corresponds to a bond angle of 109.5. 109.5 degrees. Perfect. Now what we need to do is get the molecular polarity. It's going to be either polar or non-polar. In order to do that, we really need to build that model. So we're going to go back to the model that we had before. We're looking at our key. We're going to add one more element, and that is a chlorine, which is green, and it has a single hole in it. So has three hydrogens and then a chlorine. So hopefully you can see that this represents that chloromethane. And I'll just show you that here. It should have bond angles just like the methane molecule. Those bond angles are 109.5. So here is that chloromethane molecule. So now we're going to ask the question is, are all the outside things the same, or is there something that's different about them? Well, hopefully you can see that most certainly not all the white things are the same, right? There's this green thing that makes it different. So we're going to say, quote, different. Now, different is actually not an answer. If it is different, then it is asymmetrical. If it is asymmetrical, then it is polar. And our true answer here in this column is it's polar. That's the answer because it's asymmetrical. All right. Perfect. You guys are doing a fantastic job. We have three more only to do on this. I hope you're following along and holding on tight. I'm going to pull this molecule away. Just as a little bit of a self-advertisement, I am the Crazy Hat Chemist. Oh yeah, folks, that's right. I'm the Crazy Hat Chemist, and please like, subscribe, show me some comments, and if you've noticed, the comment section is going out of control. Out of control. I noticed that too. Okay. All right. Anyways, so I'm going to pull this up here, move this up. And now what we're going to do is dichloromethane. So our formula here is CH2Cl2. So again, what we're going to do is we're going to go back to our periodic table. We're going to find carbon. How many carbons? There's one carbon. And we're going to find the valence electrons on carbon. That would be 4 from our periodic table. So 1 times 4. The hydrogens, there are 2 of them. So 2 times the valence electrons for hydrogen is 1. So 1. Okay, there are 2 chlorines. So I'm going to multiply the number of valence electrons of chlorine. That's right there, which is 7. 7. Perfect. So what we're going to do is we're going to do the math on this here. Beautiful thing here. So we got 1 times 4, that's 4. We got 2 times 1, that is 2. And then we got 2 times 7, that is 14. We're going to add all these up, that equals 20. And then every single time, we're going to divide by 2. So we're going to get 10 pairs. We're always working with pairs. The next part of this whole process is finding the least electronegative element. The least electronegative element will be the central element. Again, what are we doing? We are following these rules in order, right? The sequential steps for drawing Lewis dot structures. We first added up, summed up the total number of valence electrons. We're going to determine the central element, which is the least electronegative element. It cannot be hydrogen. So I'm not going to do the hydrogen. It cannot be the central element. So it's either going to be carbon or chlorine. And we're going to go back to this over here. We already determined carbon is farther away from fluorine than chlorine is from fluorine. So carbon will be the central element because it is the least electronegative. So the carbon is king. It goes in the center. All right, and then what we do is we place the other, so this is the A in our axe-like structure. We can actually write that up here in advance. That's A in our axe-like structure, which is the central element. The next one is going to be the hydrogens and the chlorines. And again, just like what we did on the chloromethane, we can do this in any order we want to. So what we can do is we can do chlorines right next to each other. We can do chlorines opposite each other. We can do chlorines. We can do chlorines. There's lots of different possibilities here. Okay. Any possibility works. So hydrogen, chlorine, chlorine, hydrogen. It doesn't really matter. We could have had the chlorines opposite each other, or we could have had them adjacent to each other, just like it is there. Perfect. These are going to be the hydrogens and the chlorines are going to be the X's. How many of them are there? 1, 2, 3, and 4. There are 4 of them. Okay. Now what we're going to do is we're going to place these 10 pairs of electrons. Again, we are following the rules here. We're going to first place a pair of electrons between the central A and the surrounding outside atoms as X's. So that is 1, 2, 3, and 4. Again, I'm following the same pattern of 3 o'clock, 6 o'clock, 9 o'clock, and 12 o'clock in the placement of the atoms and the placement of the electrons. The next is I've used up 4 of my 10 pair. I have 6 pair yet remaining of electrons. So if electron pairs or a pair remain, place pairs of electrons on the surrounding outside atoms X as lone electron pairs or non-bonding electron pairs. Just to clarify, see this hydrogen? It has 2 electrons. That's a duet. I'm done. I cannot do that thing right there. That is bad. So don't do that. Don't put an electron pair on the outside of a hydrogen. It already has a duet. You don't want 4 electrons. So I'm left with placing, after these 4, I have 5, 6, 7, 8, 9, and 10. I've used up all my 10 pairs of electrons. I actually have not done 3C. If electron pairs remain, place the remaining pairs of electrons on the central atom. I don't have any electron pairs remaining, so I cannot place them on the central atom. I need to verify the octet and duet rule. The duet rule is right here with hydrogen, the octet rule for other elements. So that's 2, 4, 6, 8. That's an octet on this 6 o'clock chlorine. On the 9 o'clock chlorine, 2, 4, 6, 8. That is an octet. On the central carbon atom, I need an octet. 2, 4, 6, 8. Bingo. All right, so I'm going to erase all those circles because they don't really belong there. I don't actually draw those circles out. Personally, I just do that in my head, but that's entirely up to you how you want to do that. That's really not part of the answer. All right, cool. We've already done our AX4 by doing this. There's A for that central carbon, X1, X2, X3, X4. There are no lone pairs on the carbon. I'm going to go over to my handout here and say, what is AX4? That is tetrahedral. And what is the bond angle? AX4 tetrahedral 109.5. 109.5 degrees. Perfecto. Now we need to build the model. Okay, so we're going to be basing it on the similar model here, but I got 2 chlorines to work with this time. So we're going to get 2 green chlorines and we're going to make our model. So here is our model. And some of you might be asking, well, crazy hat chemist, well, what if we put the chlorines opposite of each other? So this is what we're going to do. I'm going to hold this here really tight, okay? And I'm going to take these 2, this chlorine and this hydrogen, and flip them. So I'm going to take this off right here, okay? I'm going to do this here, right here. I'm going to take this one off right here. I'm going to place this hydrogen here. I'm going to place this chlorine right there. And I'm going to ask you, hey, is that any different than what I had before? The answer is no, it's not. It's actually the same. So it's the same structure that we had before. So there's no way to actually have the chlorines either adjacent or across from each other. They're actually always going to be adjacent to each other. And that's just because that this is a tetrahedral structure. This is not a flat structure like what it shows on paper. On paper, it shows a flat structure. It is actually not a flat molecule. It's a 3-dimensional molecule with a bond angles everywhere of 109.5. So the next question is, are the atoms attached to the central atom? The central atom, are the atoms attached to the central atom? Are they the same or different? Well, I got 2 greens and 2 whites. Those seem to be, quote, different. And of course, that would be asymmetrical. And if it's asymmetrical, that means it's polar. That's right. It is most certainly polar. Okay. Let's see. We got 2 more to do. And we are moving right along. Hey, by the way, I'm going to do a little bit of self-advertisement. This video is sponsored by none other, the one, the only, the Crazy Hat Chemist. Please like, subscribe. I am the Crazy Hat Chemist. I am the sponsor of this video here. I don't actually have any sponsors besides myself because I'm that, yeah, popular. Maybe someday. All right, so the next one is trichloromethane or chloroform. We're going to be doing the same thing that we did on all the previous ones here. Okay, so hopefully this is you're following nice and tightly along with this problem here. So how many carbons do I have? I have one carbon, one carbon. How many valence electrons in carbon? How many valence electrons in carbon? Four. So four equals. I got one hydrogen. How many valence electrons in hydrogen? One valence electron in hydrogen. One. So this is a four. One times four is four. One times one is one. Then chlorine. How many valence electrons in chlorine? Seven. So there are three chlorines, seven valence electrons, and that is 21. So we are going to add all this up. We got 21, we got 1 and 4, and that's going to be 26 total electrons. And then we are going to divide that by 2. So now we're going to have 13 pairs. Again, we always work in pairs. Okay. So what element cannot be in the center? That's correct. Hydrogen cannot be in the center. So I have two choices. I have either the carbon or the chlorine. So I'm going to look at my periodic table here, and just like before, there is carbon. Its distance from fluorine is this pink line. There is chlorine. Its distance from fluorine is this orange line. Which line is longer? The pink line is longer than the orange line. Therefore, carbon is going to go in the center. That's right, folks. Carbon is king. Carbon goes in the center. Then what we do is just like before, we're going to do X marks the spot like we are a pirate or the sign of the cross or something like that. Okay, and then we're going to place the other elements around it in any way, shape, or form. So we have one hydrogen and three chlorines. You can do it any way you want to. What do you want to start with? That's right. You can start with that. Exactly. So I'll start with the chlorine. I'll start then with the hydrogen, then another chlorine and another chlorine. The order doesn't matter. I'm going to erase all the dashed lines that I had on there. Get rid of that mess. All right. Now what we're going to do is we are still, as always, following the rules. And those rules are we added up this total number of electrons. We determined the central element, which is the least electronegative, but never hydrogen. We're going to place the other atoms in the faces of a clock like 3, 6, 9, and 12 o'clock. We're going to place pairs of electrons between the central A and the outside X atoms. Pair of electrons, that's 1, 2, 3, 4. I've used 4 of my 13 pair. Okay, so my 13 pair, I've used up 4. That means I have 9 pair yet remaining. The next rule is to place pairs of electrons on the outside atoms as the X atoms, and these are lone pairs. So I've used up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and finally 13 pairs of electrons. Do we have any more electrons? No. We're going to verify the duet rule for hydrogen only. That's 2. We're going to verify the octet rule for all elements other than hydrogen. That's 2, 4, 6, 8. That's an octet. An octet for 2, 4, 6, 8. Yes, that's an octet. An octet, 2, 4, 6, 8. And finally, an octet for our central element, 2, 4, 6, 8. That's an octet. Everybody has an octet. I'm going to erase all that because that actually doesn't belong. I do that inside my head, not to confuse you. The central element is the A in our X. The outside elements are X's. How many outside elements do I have? 1, 2, 3, and 4. That corresponds, that AX4 corresponds to what? None other. AX4 corresponds to tetrahedral. Tetrahedral. And tetrahedral AX4 tetrahedral corresponds to 109.5. 109.5 bond angle. Oh, yeah. Perfect. Now we need to get whether this is polar or non-polar, and we need to build the molecule again. There are going to be 3 chlorines and 1 hydrogen. So we're going to rip off one of those hydrogens from the previous one, replace it with a chlorine, and then here's what we've got. Here's our model. Hopefully you see that model. It has bond angles of 109.5. It's a tetrahedral arrangement of around that central atom. I'll place that right here. And I'm going to ask the question, are the X's that are surrounding the A, are they the same or different? They are most certainly different. Different corresponds to asymmetrical. And asymmetrical corresponds to polar. Polar is the answer. Different is not the answer. And then when you move on in chemistry, the real answer is asymmetrical yields to polar. Polar is the answer. If it's asymmetrical, it's polar. If it's symmetrical, it's non-polar. Okay, perfect. We've got one more problem to do, folks. Hang on tight. Here we go. All right. Our next problem here is carbon tetrachloride. So how many carbons do I have? 1. How many valence electrons in carbon? Well, 4 valence electrons in carbon times 4. That equals 4. Okay. And then we have chlorines. We have 4 chlorines. 4 chlorines. How many valence electrons in chlorine? 7. That's 7. So 4 times 7, that is 28. We're going to add that to the 4. That's a total of 32. And what do we always do? We always divide by 2. So that's 16 pair. So I have 16 pairs of electrons. Now we're going to ask ourselves, what's the least electronegative? That is going to be the central element, the least electronegative between carbon and chlorine. Well, we've been doing this the whole time here. We got a carbon, we got a chlorine. What is farther away from the fluorine? Carbon is. That is the least electronegative, and that is the central element. So the least electronegative is the carbon. The chlorines, there are 4 of them. They're going to go around the 3 o'clock, 6 o'clock, 9 o'clock, and 12 o'clock positions. We're going to follow the same set of rules that we've been doing before. That is to place a pair of electrons between the central and outside element, the 3 o'clock, the 6 o'clock, the 9 o'clock, and the 12 o'clock position. We have remaining electrons. So we have used up 4 of our 16 pair. We have 12 left to do. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16 total pairs of electrons. I'm going to verify the octet rule. 2, 4, 6, 8. That's an octet. Verify the octet rule. That's 2, 4, 6, 8. That's an octet. Verify the octet rule. That's 2, 4, 6, 8. Verify the octet rule. That's 2, 4, 6, 8. Verify the octet rule on that central carbon. 2, 4, 6, 8. That is satisfied. Erase all that. I do that in my head. I actually don't write that on paper. Okay. And now what we're going to come up with is our acts. The A is the central element. There's only one of those. There's always only one central element. The X's are the outside elements, and I have 1, 2, 3, 4 outside elements that are physically attached to that A. There are 4 of those. You should see a trend on this particular worksheet. Don't think that it will be the same for all of them. And that is AX4 corresponds to tetrahedral. And the bond angle for AX4 is 109.5. Then we're going to build the model here, and we're going to take off that last remaining hydrogen, and we're going to replace it with that chlorine. And you should see that is what we get right there. That is perfect. That is what we're looking for right there. Okay, and you should see now this time we have all the outside elements that are green. Those are the same. That corresponds to symmetrical. And that corresponds to non-polar. Non-polar is actually the answer in this. Okay. All right, folks. So that is really the conclusion of this video. We have built a stamp for each and every single one of these, and hopefully you understand that. And I am the Crazy Hat Chemist, and please like and subscribe, like this video, subscribe to my YouTube channel. I'll zoom on out so you can see the entirety of this worksheet here. I don't have all the models built here, but you can at least see this one right here. Okay, there is that carbon tetrachloride. All right. And let's just go through some of them here. Let's go for methane. We'll build methane here real quick as a kind of a final conclusion. We'll build them all here and we'll show them all to you so that you get kind of the idea here. Uh-oh, I just threw away my tetrachloride on the ground. We don't want to do that. That's some toxic stuff. Don't drink it, eat it, or yeah, whatnot. All right, so this is methane. This is carbon tetrachloride. All right, so what is chloromethane? This is chloromethane. Perfect. What is dichloromethane? This is dichloromethane right here. And what is trichloromethane or chloroform? There is trichloromethane or chloroform. These are different, and this one's different as far as the atoms on the outside is polar. These are different atoms on the outside are polar. I hope you have a fantastic day. Thank you very much for liking, subscribing, and making comments. I am the Crazy Hat Chemist. I love you all, and I'll see you next time. Bye for now.